Okay, so here we are in the last lecture for chapter 12. Hopefully you've been learning much about alkenes, alkynes, and the different aspects of reactions they undergo, and cis-trans isomerism, and all that good stuff. So now we're ready to close out the chapter with our discussion of aromatic compounds. Now, when we mention aromatic compounds in chemistry, it doesn't necessarily have the connotation it might have in everyday language where it has a pleasant smell, right? That's what we normally think of with aroma and aromatic. Just like organic chemistry itself, we're not talking about the organic like at the grocery store. We're talking about hydrocarbon-containing substances. Here with aromatics, we'll see we'll be talking about benzene ring-containing substances. All right, so as I just mentioned, benzene is a common theme with aromatics, so the benzene structure is important to recognize and understand. Benzene itself has 6 electrons shared equally among the 6 carbon atoms of its flat planar ring, right? They're shown here as alternating double and single bonds, but it doesn't really behave like that. It behaves much more like an alkane, so it doesn't undergo addition reactions where we would expect something with true double bonds, as we've seen, to undergo addition with either hydrogen or the halogens, as we mentioned earlier on in this chapter. Here, benzene, although we show it as alternating double and single bonds, it's not nearly as reactive as true double bonds would be. So sometimes we'll represent it simply as a hexagon with a circle inside to show that idea of benzene not being alternating double and single bonds, but rather being sort of like a bond and a half among each of the carbon-carbon bonds in that ring. It's even if you measure the bond lengths, right, they're identical, although we'd expect for alternating double and single bonds, we'd expect shorter double bonds and longer single bonds, and that's not what we see. Benzene's a very special substance, and it gives rise to these aromatic compounds. Okay, so originally the term aromatic does get its name from those fragrant odors, and that has to do with the fact that at the time of the discovery of benzene, many of the compounds that had benzene in parts of their structure did have these fragrant odors. So that's how we originally got the name, although now that's not necessarily true. We now understand much more about benzene rings and compounds that contain benzene rings, and not all are aromatic. Some don't really have much smell at all. Some have unpleasant odors. So although the fragrant odors are where the aromatic compounds got their name, it's not necessarily the case anymore. Here in our image, we see some pleasant smelling substances. At least most of us would consider them pleasant smelling. If you like anise, that licorice type odor is due to anisole. We've got tarragon being also due to an aromatic compound largely for its odor, and thyme has thymol as its principal aromatic compound. Here's some other common aromatic compounds. TNT, for those fans of high explosives, this is 2,4,6-trinitrotoluene officially as its IUPAC name, and therefore abbreviated by TNT, and that doesn't have much odor at all. Certainly it's not the odor we're after for that one. It's the explosive nature of it is a high explosive detonated in the presence of a primary explosive. We have ibuprofen, right, and that's a common pain reliever, and there's its structure with that sort of central benzene ring. We have aspirin, known much longer than ibuprofen. Aspirin isolated from white willow bark, and we see its structure also has that prominent benzene type ring. And finally, vanillin, the principal component of vanilla flavoring, and certainly natural vanilla has lots of vanillin. The artificial is almost exclusively vanillin, and there we have its structure with its benzene ring. So lots of different applications, different levels of odor, if any, but all common with that structural feature of the aromatic ring, the benzene type ring. Okay, so now that you've seen how prevalent this benzene type ring is in a number of compounds, we've got to deal with the fact that we need a way to account for it in the name, right? If you've learned nothing so far, you've learned that nomenclature relies on us being able to quickly and conveniently identify those key components of a structure. So if we're just dealing with benzene as the parent and some substituents maybe, obviously if it's just plain old benzene, we call it benzene. But as we see here, we have one side group here for methylbenzene, more commonly known as toluene, and unfortunately that's a common name that's going to be very, very common. So you'll rarely see methylbenzene, you'll almost always see it referred to as toluene. And then we have chlorobenzene, where the methyl group has been replaced now with a chloro group. Again, the other positions that we don't show are hydrogen atoms there, because we do need 4 bonds to each carbon atom, and so there is a hydrogen at each of the other positions not shown here because we don't show hydrogens, right? At least not in skeletal structures. Okay, so again, the benzene ring has been known for some time, and it's had lots of common derivatives and therefore some common names that, because they've been used so long, they're not going to go away anytime soon. And unfortunately, oftentimes the common name is the more pronounced and therefore an important name to know, although we want to try to always know the IUPAC name as well. So we have a single substituent, there's often common names that are used, or you can name them officially as benzene derivatives, as we see below in parentheses. So we already mentioned that methylbenzene is more commonly known as toluene. We see here aniline, which is technically aminobenzene, but we have aniline as a very common name in this area, the southern tier of New York. There was General Aniline and Film, GAF, was a big company in its day, and aniline was front and center in that name, I guess more center than front for GAF. Finally, instead of hydroxybenzene, you're much more likely to see that last compound on our right known as phenol, and it's important in terms of disinfectants, and it was used in hospitals for a long, long time. It's still either phenol or derivatives often used as disinfectants, even in this modern day. So lots of important applications, and these 3 have been known for quite a long time, and therefore the common names tend to predominate. All right, so once we get more than one substituent attached to that benzene ring, then we have to start to think about how we're going to specify those substituents on the ring. So the rule is we number the ring to give the lowest numbers to the side groups, that's the IUPAC nomenclature, or we can use prefixes to show the arrangement of the substituents on the ring. So common name, for instance, for substituents that are right next to each other would be ortho, or according to the IUPAC nomenclature, we do 1, 2. If they're separated by a hydrogen, then we have now the meta, or the 1,3 variety. And finally, if they're at opposite sides of the benzene ring for the substituents, they're known as para, or using IUPAC 1, 4. So we can show the relationship on the benzene ring for the 2 substituents using either of these. Of course, I prefer IUPAC, but you're going to see those common ones almost as frequently, if not more so, when dealing with aromatics. All right, so let's look at a few examples. So here at the extreme left, we have the first and third carbons have the substituents. So instead of naming it as 1-methyl-3-chlorotoluene, or benzene rather, we look at that common name of toluene, which is the benzene ring with the methyl group, and then we see that there's also a chloro group. So we can just refer to this either by IUPAC rules as 3-chlorotoluene or as meta-chlorotoluene. Either way, either the number or the letter gets a dash there before we write the name. The middle structure there has the chloro groups on opposite sides of the benzene ring. So this is known as either 1,4-dichlorobenzene or para-dichlorobenzene. And that compound in particular is sometimes used as mothballs. So that's that characteristic odor that you might know. And of course, it's unpleasant to moths, and that's why it was used in that application. But it's 1,4-dichlorobenzene, and that involves the substituents being on opposite sides of the ring in the 1,4 position. Finally, on our extreme right, we see the substituents right next to each other. Because phenol is the common name for that benzene ring with the OH group, we refer to this as a phenol with a chloro group, and in this case it happens to be either 2-chlorophenol or orthochlorophenol to indicate that 1-2 relationship for the substituents on the first and second carbons. So not too bad. Hopefully you're catching on quickly to the nomenclature rules for aromatics. Now, when both substituents are methyl groups, you'll often see the common name xylene used instead of referring to the compound as a dimethylbenzene. So if methylbenzene is known as toluene, dimethylbenzene is commonly known as xylene. So we see in our different structures here, we have the 1,2, 1,3, and 1,4, or more commonly ortho, meta, or paraxylene. So right on top IUPAC, the 1,2, 1,3, or 1,4 dimethylbenzene is the IUPAC name, but ortho, meta, or paraxylene is more likely how you'll see these referred to by that common name. So moving right along, what do we do when we have the aromatic compounds with 3 substituents? Well, we continue usually with the IUPAC name only. We don't have any special common names here, fortunately, so we tend to be using the IUPAC numbering part rather than the lettering for our naming. So we see here at the extreme left, we have 3 chloro groups in a 1,3,5 position. So this is 1,3,5-trichlorobenzene. In the middle, we have a methyl group, a chloro group, and a bromo group. So of course we go alphabetical, although the methyl group is the most important. That's what makes it toluene. So we have to decide then which way we number. And of course the rule is we number around the ring so that we get the lowest overall sum of the substituents. So rather than going clockwise and hitting, still bromo group would be in the 4 position, but that would make chloro in the 6th position. Instead of going clockwise and getting that 4 plus 6 to equal 10, we start at the methyl group carbon of the toluene and we go counterclockwise to get now chloro in the 2 position and bromo in the 4 position. Then according to nomenclature rules, we have to name in alphabetical order, so that's why it's 4-bromo, 2-chlorotoluene. And finally, where we have the different substituents there on a toluene, we have now 3 substituents plus at the toluene itself. This would be 2,6-dibromo, 4-chlorotoluene. We had to get to 6 there because if we went clockwise or counterclockwise, we'd still end up with the same numbering scheme. So hopefully not too much more difficult as we add additional substituents here. All right, I think it's a good time to pause for a learning check. Make sure this is making sense to you. In this learning check, you're asked to select the correct name or names for each of the following compounds. So we have 2 different compounds, and then we have 3 multiple choice options, and you can select 1 if there's only 1 that's correct, or you could select 2 if there's 2 that are correct. Again, if there are more than 1 correct name for a given compound, it's because those common names are so prevalent, as well as the IUPAC name. So go ahead, stop the video here, select your name or names for each compound, and then start back up to check your work. Okay, so for that first compound, there was only the one option that would work, and that was B, chlorobenzene. For the second compound, we can refer to it as B, 1,3-dimethylbenzene, but being a dimethylbenzene, we know that xylene is also a common name for it, and this happens to be metaxylene for the 1,3 position. So if they were 1,2, it would have been ortho. If they were 1,4, it would have been para, but this is 1,3, so it's therefore metaxylene. So if that didn't go so well, if you got tricked by some aspect of that question, please do try some other naming questions for the substituted benzenes, and definitely reach out to me if it's still not making sense. So hopefully naming from a structure is getting more comfortable. Let's follow up with a learning check here that asks you to draw the condensed structural formulas of each of the following, and this will give us a better idea of how well you can translate names into structures, a very important thing to be able to do, just like getting a structure and arriving at its name. So we have two here. If you would pause the video while you complete that task and start back up to see how your structures compare to the correct answer. Okay, so for number one, we draw the benzene type ring, and again, it is preferred to draw the hexagon with the circle rather than the alternating double and single bonds to get that idea home that the benzene ring is not a single bond double bond relationship, but rather a 1.5 bond shared delocalized grouping of electrons. And so the 1,3 dichlorobenzene is going to have the benzene type ring, and then in positions 1 and 3, as you define them, we would have the chloro group. So it may not look exactly like mine. It might be a rotation of what I have up there, but it should be something with the 1,3 relationship of the chloro groups. Number two, instead of saying 1,2, we say orthochlorotoluene. We're using the common names, making sure that you can decode a common name just like an IUPAC name. And so here, again, we've got that benzene ring. We've got a methyl group to make it toluene, and then a chloro group right next to it for that ortho relationship. So again, if this didn't go so well, please do try some additional practice with this skill of taking a name and drawing a structure, and reach out to me if you continue to struggle. All right, one last learning check before we leave this chapter, and here you're asked to identify the organic family for each of the following. So we have A, B, C, D, and just give the main type. Is it an alkane, an alkene, an alkyne, an aromatic? Those are the 4 different groupings we know so far, so decide to which family each of those structures belongs. Okay, so A, we see that double bond at the end. Hopefully that triggered in your memory the idea of an alkene, because that's the family that that particular compound belongs to. For B, we have an alkane, right, because there's no double, triple bonds or benzene ring present. It happens to be a cycloalkane because it is a ring, that's cyclopropane. But just recognizing that it's an alkane for right now as opposed to an alkene, alkyne, or aromatic was probably the key aspect of that particular structure. Then C, you notice that triple bond at the end, so that's an alkyne. And finally D is good old benzene, which is our characteristic aromatic compound. So hopefully you were able to identify those different groupings. If not, please do continue to practice, because it is important to be able to recognize the family in order to be able to give the correct name. And finally, before we leave our topic of aromatic compounds, let's discuss a few key properties of aromatic compounds. Aromatic compounds are typically classified by higher melting and boiling points than you'd expect for carbon groups of that size, and that has to do with that flat symmetrical structure of the ring, the fact that the rings can align to do what's called pi stacking. They have lots of pi cloud above and below the plane, and the pi cloud of one aromatic ring can interact with its neighbors and give a nice strong interaction that accounts for those strong intermolecular forces. They also tend not to be soluble in water, although sometimes if they have the right substituents, like phenol had that OH group right off of the ring, or if we're dealing with things like benzoic acid, a carboxylic acid group right off the ring, then those polar side groups can make the usually nonpolar benzene ring soluble in water. They also have that very stable aromatic bonding system, and that's why they don't tend to undergo addition reactions. You have to have some pretty severe conditions to coax a benzene type ring into any sort of reaction, so we expect greater stability. If a side chain, a substituent on the benzene ring, has a double bond or triple bond, then it would undergo the classic behavior. But again, an aromatic ring is not an alkene, it's a special case known as an aromatic. They also tend to be flammable, just like the other hydrocarbons. So even though they have that stable bonding system, even though they're resistant to many reactions that would break up the aromaticity, the 1.5 bond nature within the ring, one thing they will do, like the other hydrocarbons, is burn. They tend to burn with a very sooty flame, though, so it's not a clean burn, but they will burn, and that's one key reaction that they do undergo is combustion. All right, so hopefully we've distinguished the aromatics from the other unsaturated compounds because, again, we show double bonds, alternating double and single bonds sometimes in the benzene ring, but it's not your classic alkene. It's its own special case known as an aromatic. If you still have questions about aromatics and you've gone to the reading and you're not finding what you need to know, please do reach out to me. Otherwise, we'll assume things are going well, and we'll see you in Chapter 13.